Welcome to lecture 9 of derivative securities. Today's topic is on further discussion of options. So we will focus on options that's paying dividend yields, actually continuous dividend yield. So for those for the underlying asset that may possibly have continuous dividend yield. Today we are going to focus on stock indices, currencies, and actually future contract, which is a derivative contract itself. Also one more word about the options on futures. So for options on futures, since it's a derivative of a derivative contract, so you can basically it's just like a multi-layer of derivative. Then let me quickly go through the learning objectives. So for those options on assets paying a continuous dividend yield, we will focus on adjusting the boundary conditions we learned earlier, like the upper and lower bounds, and also the put call parity relation we learned in earlier lectures, to reflect the effect of dividend yield. We are also going to adjust what we have learned in lecture 8, the binomial model and the Black-Scholes model to reflect the effect of continuous dividend yield. Then for the specific examples we're going to tackle with today, the options on indices. So they are approximately paying continuous dividend yield because for the stock indices. So because the different stocks in the stock index portfolio would be paying out dividends on different dates. Therefore, on average, on every date, you are receiving dividends. Then for options on currencies, also, by the way, in this lecture, we are expressing the dividend yield as Q. So obviously for stock index, Q is Q. Then for options on currencies, recall that we have two interest rates, right? One interest rate is for the local, for the domestic currency. Then the other interest rate is the interest rate, the risk-free rate for foreign country. So here, for options on currencies, its dividend yield Q is actually just the RF, the risk-free rate of the foreign country. So for options on futures contracts, so we'll in later slides we'll briefly discuss why actually for the futures contract Q is can be viewed as R. So R would be the interest rate, remember, the risk-free rate. Then we will plug in that R into the Black's model, the Black-Scholes model, to value those futures options. Also, one more thing about the options on stock indices. Recall that in previous lectures, we use those options on stock indices to kind of eliminate the exposure to the market, for the short term, right? So in that hedging example, which we did in the previous lectures, we showed that the number of contracts would be equal to beta, the number of options contracts we use would be equal to beta times the portfolio value divided by the value of a single future contract, right? So sorry, the value of a single option contract. Then also for the beta here, beta, that's a optimal hedge hedge ratio, remember? Like if we are dealing with stock indices options. But today we are going back to that example, but we are also going to show how to determine the exercise price, the strike price of the options with the presence of dividend yield. Actually with dividends. Before I go to the content itself, let me quickly discuss the intuitions of impacts of dividend yields on pricing. So there are two ways to think about that, think about the impact. So one intuition is that like the dividend yield can like lead to cheaper prices, right? So like when time evolves, the price trajectory is going to be lower, right? So in that case, therefore, so let me just actually scroll to the next page. So in that way, actually the asset price starts at price at 0 and pays a dividend yield Q. Also, it's going to have the same probability distribution as the asset price starts at price at 0 times e to the power of minus qt and provides no dividend income. So like the intuition is just that like the dividend yield, like the stock with dividend yield is just like the stock start with a cheaper price, but with, of course, with the same return R. So like for this intuition, what you do is that you just keep R remain the same, but you basically assume that your price just starts lower. Yeah, so things like the dividends are actually going to reduce the stock price along the like price evolution. So you can just reflect that at the beginning. Yeah, that's the first intuition. And the second intuition is that basically you assume that the price, which is actually the realistic scenario. So the realistic scenario is that the like the stock price, they all starts from S0. But now for the like for actually the spot price. So the spot price, they all start at 0. But for the option with an underlying asset that's paying like the continuous dividend yield of Q, now actually its capital return is lower. So actually in the Black-Scholes model, let me check. So in the Black-Scholes model, we are using the first intuition. So for the binomial tree, we are using the second intuition here. So so basically you just like you just go with a realistic scenario where the spot price just starts with like the S0. Now the capital return, since in the binomial model we care about the capital return, we don't care about the total return. So since R is reflecting the total return, so for underlying asset that's paying dividend yield Q, then we know that capital return plus div yield would be equal to R. So if you have like with the previous scenario, we have dividend yield equal to 0, right? Therefore, the capital return is just R. But for today's examples, since we have Q not equal to 0, therefore capital return would be equal to R minus dividend yield, therefore R minus Q. So therefore, in the previous pricing relationships we learned, more specifically, actually just a binomial model, we just replace R with R minus Q. So also, when we are using the first intuition to the boundary relationships or the pricing relationship, we just replace S0 with a lower price of S0 times e to the power of minus qt. So let me using words to describe the intuitions again. So the first intuition is just that for dividend paying underlying asset, you just assume that actually the return remains the same, like the capital return remains the same. And then it just like remains the same to be R. And then its price just starts off lower. So since it's actually going to have the same probability distribution as a realistic scenario where you start off at a price of S0, but you ended up having lower capital returns, it's just the same as you start off at a lower price, but you have the capital return still being R, not subtracting the dividend yield. So that's the first intuition. It's just that dividend is reducing the prices. So like when time evolves, therefore you can just put that impact at the beginning. So you can just assume that the price is reduced at the beginning. Hopefully that's more clear explanation. Then for the second intuition, it's just that it's just a realistic scenario. So you just start at S0. Now the capital return is reduced by the dividend yield. So instead of R, now the capital return is total return minus dividend yield, therefore R minus Q. So now let's move on to, I will just skip this page because we already discussed this. So let's go to the boundary conditions and the put call parity. So recall that for the calls, the lower bound was maximum of S0 minus K times e to the power of minus RT or 0, right? So here we are using the first intuition. So we replace our S0. So we replaced S0 with lower price, S0 times e to the power of minus qt to get the new boundary condition. Also, recall that in the previous lectures, we showed that the upper bounds was, for call options, was that the call option price is going to be no greater than S0. Again, we get this new inequality for the continuous dividend yields paying underlying asset. We change this boundary condition again by replace S0 with S0 times e to the power of minus qt. Then for the put options, we recall that the lower bounds was K times e to the power of minus RT minus S0. So this one, that's the original sorry, actually the maximum of that, the maximum of this term I just described, or 0. So we actually adjusted that by, again, just changing S0 to be S0 times e to the power of minus qt. Easy, right? And as for the upper bound, since for the put options, the upper bound don't have any S0 involved, therefore it remains the same as what we have from previous lectures. Then for the put call parity, also we have S0, remember? Like the put call parity is C plus K times e to the power of minus RT is equal to P plus S0. Now we just like replace S0 with S0 times e to the power of minus QT. Also, don't forget about this discrete version we discussed in previous lectures. So for the discrete dividends, we're just subtracting. Whereas for the continuous dividend yield, we are actually changing S0 to be lower, like to become S0 times e to the power of minus qt. Now onto the risk neutral valuation. For risk neutral valuation, here we are not using the first intuition anymore. So as I discussed earlier, we are actually using the second intuition, just that the dividend paying underlying asset, they are having a, like, if the total return remains equal, being R, those dividend paying, like continuous dividend paying underlying asset, they are going to have lower capital returns. And that's lower capital returns is actually R minus Q. So hopefully you guys still remember those two pricing relationships for the binomial tree. So for the binomial tree, basically S0 would be the discounted value of the expected value of ST, right? So it's like the spot price today is a discounted version of the expected value of the spot price at maturity date. So that's the meaning of this equation. But actually, like for the original version without the dividend yield, we know that it's actually e to the power of minus RT times e ST, right? So here for the underlying asset, we know that R is being lower. So not really R being lower, it's a capital return that's being lower. So instead of being R, now it actually becomes R minus Q. So therefore, for this first equation of the like binomial model, we replace R with R minus Q for the spot. Let me actually get rid of that. Then for the so we also have another equation for the valuation of the like of the option contract, right? So F here stands for the price of the options. Since we don't know if it's call or if it's put, therefore we represent its value with F. So F0 would be equal to like the discounted version of its value at maturity date. Actually of its expected value at maturity date. Here the R remains the same. Actually, we don't change it into R minus Q. Like because the investment in the option itself doesn't generating any dividend yield, right? So its return should be remaining like its required return should be remaining the same. So, yep, that's the only thing we changed. So we only changed like for the first equation. Next first equation, like this new version of the first equation, we can derive the new risk neutral probability. So for this risk neutral probability, recall that we express SU as U as US0 and SD as D as 0, where U is greater than 1 and D smaller than 1. So if we take into account of that, and if we solve for P, so we solve for P from this equation, from equation 1, we get that P is now equal to e to the power of R minus Q times T minus D, then divided by U minus D. So for the original version, we actually have e to the power of RT minus T divided by U minus D, right? So now we actually just replace that R with R minus Q. Then for the valuation of the options contract, it's the same. Like we just use a P we just get. So we use P times the times, since like the risk neutral probability is measuring like in the risk neutral world, like the probability of going up. So it's associated with like the underlying asset going up. Therefore, we use P times FU, and then plus 1 minus P times FD. So that's the expected value of the derivative contract, right? At the maturity date. Then you basically discount that expected value back to time 0 by timing e to the power of minus RT. So for the Black-Scholes model, so we like unlike the risk neutral valuation like part, so unlike that part where we are using like the intuition of lower return. So like for the Black-Scholes pricing formula, again, we are using like the intuition that they now we basically start off with a lower stock price. So instead of S0, now for the options with dividend yields, the S0 is replaced with S0 times e to the power of minus QT. So let's see how that influences the pricing relationship. So for the expressions of C and the P, like the call price and the put price, it's straightforward. We just change anything associated with S0 to be S0 times e to the power of minus QT. Let me use. So this term here, that was like, if you go back to lecture 8, you'll find out that's just S0. And also for the put price, also like for the second term, it was S0 in lecture 8 as well. So now we just replace them with lower prices. Then, but the D1 expression changes a bit. So so we can still express D2 in terms of D1. So D2 would be equal to D1 minus sigma times square root of T. Now let me show you guys how like this expression of D1 actually changes a bit. So again, like you guys will notice that in lecture 8, this numerator was actually S0. So now we replace S0 with S0 times e to the power of minus QT. But we can actually further modify this expression. So recall that ln AB will be equal to ln A plus ln B. So this is some feature associated with natural logarithm. So by applying that computation rule for natural logarithm, we can basically get this e to the power of minus qt outside of the bracket, right? So therefore, ln S0 times e to the power of minus qt divided by k, close bracket, would just be equal to ln S0 divided by k, and then plus ln e to the power of minus qt, and you close bracket. So that's actually just ln S0 divided by k, you close bracket, and then minus q. So you plug in this equation back to the numerator for D1, like the entire numerator here for D1. Then you get that, now instead of ln sk divided, ln S0 divided by k plus r plus 0.5 sigma square times t. Now we have an additional term inside the bracket. That's minus q. So yeah, that's what's different in terms of the Black-Scholes pricing formula for the underlying for the options on underlying asset with continuous dividend yield. Now, now let me go to the pricing for index options. So for those examples, we're just applying the Black-Scholes pricing formula, like here, like this general. So this is the general pricing formula for all the options on like underlying asset with continuous dividend yield. Then we're just going to apply that pricing formula to those examples, like to the examples of index options, currency options, and future options. So for index options, we actually have already derived this, right? So like for the binomial model, so what really changes is only the risk neutral probability instead of r. Like now it's e to the power of r minus q times theta t. So instead of like e to the power of r times theta t. So the only thing different here is just here. And the option contract is still discounted utilizing R. Also the delta t here, that's just a time step. Sorry, the length of each time step. Yeah, delta t is length of each time step. And for the Black-Scholes formula, since index options do approximately has continuous dividend yield, therefore we just plug in those. Q, not really plugging, but like we just like stick to the general formula we just derived here in the previous page. Then we can actually further change that Black-Scholes formula. So for like, how can we what can we do to change that pricing formula? The answer is that we can utilize this relationship here between the forward price and the index price. So from the previous lectures, we know that every forward price or futures price can be expressed in the form of the underlying spot price. So this is what we have derived in previous lectures. So F0 is equal to S0 times e to the power of R minus QT. Then we just plug in, like we just plug in this equation. Actually we rearrange terms of the equation and then plug this equation into the Black-Scholes model. Let me show you guys how. So here what we did is that we just move the e to the power of R times t to the left-hand side of the equation. So since here we are timing e to the power of R times t, right? Therefore, if we move it to the left, it automatically becomes that we are dividing by e to the power of minus RT. Hence we have a negative sign here. So F0 divided by e to the power of RT is equal to S0 times e to the power of minus QT. Like this term on the right-hand side looks familiar to us, right? So this is a new stock price that we use for the continuous dividend paying underlying asset. Therefore, basically, remember how we are replacing S0 with S0 times e to the power of minus QT in the previous steps, right? Now we further change this S0 times e to the power of QT, minus QT, change it further to basically expression using F0. So that's F0 times e to the power of minus RT. Then you just substitute this F0 expression into where S0 was in the original version of the Black-Scholes model. So now the call price would be equal to F0 times e to the power of minus RT, then times ND1, and then minus K times e to the power of minus RT times ND2. So aside from this term I highlighted, all the rest actually remains the same, right? Of course, also for put prices, we only changed S0 as well. So we change S0 into F0 times e to the power of minus RT. Now we can also apply that trick we did with the original version for continuous dividend paying underlying assets. So we apply this trick, like ln AB is equal to ln A plus ln B. So let's apply that trick to this formula as well. So now D1 would be equal to, let me show you guys. D1 is equal to ln S0 divided by K plus 1/2 times sigma square. Oh, sorry, I forgot one term. So I'm writing the original form of BS formula, which we learned from lecture 8. So here R plus 1 divided by 2 times sigma square, and then times T divided by sigma to the times the square root of T. So here we are replacing that S0 ln S0, sorry. Actually, I already wrote it here on the right-hand side, but let me just write that again. So we are replacing S0 with F0 times e to the power of minus RT. And then divided by k. Actually, here, let's forget about the original version without dividend yield. Actually, let's write this expression as a version like as a previous version we just showed, like we just discussed, like this version. Let's just utilize this version here. Now let me go back. So let me change that into S0 times e to the power of minus qt. Then we are like from the relationship between forward price and underlying price, we can express that S0 expression into F0 expression, right? So then let me continue on writing. Plus R plus 1/2 times sigma squared times T. Then divided by sigma times square root of T. So here, actually, if you basically separate this e to the power of minus RT out, we will get that this not really numerator, but like this fraction is going to be equal to ln F0 divided by K plus 1/2 times sigma squared times T divided by sigma times square root of T. So now like both Q and R are gone. So the trick is that is basically ln AB is equal to ln A plus ln B. So this e to the power of minus RT, once you take it out, once you separate it from F0 divided by K, you'll get that it's equal to minus R. Therefore, minus R will be canceled out with this positive term. So we effectively get a numerator without R and also without Q. Now, let me get rid of that. So if you utilize this version of the Black-Scholes model to do the valuation, you basically don't need to estimate the dividend yield. So as long as you are using the forward price to do the valuation, since like in this version of the Black-Scholes model, like neither R nor Q appeared in the D1, D2. Of course, R still appears in the expressions for C and P, because like you see e to the power of minus RT, but we don't have to estimate for Q because Q do not appear in the equation once we are using the forward price. I also have this expression of the like the derivation of the numerator on the right hand side. So let me get rid of what I have written, and I will leave the right hand side as a note. So as you guys can see, here, like this expression just focus on the numerator. And for the numerator, it's just that the logarithm of e to the power of minus RT canceled out with R. Sorry, actually here, here this is equal to minus RT. It's actually canceling out with RT. So it's minus RT canceling out with RT. Now we have a specific example of index options. So that specific example is S&P 500 index options. I will leave the details for you guys to read. Like it's basically on the terms of like the terms and conditions of the S&P 500 index options. So here I'll just quickly discuss some of the features. So for index options, they are actually usually European. So you can also see this from this S&P 500 index option. So it's European. Whereas the options on individual stocks, they are usually American in practice. Also, the options, the option on index, it's usually cash settled. So you guys can see from this S&P 500 index option as well. So so the key takeaway is that index options are usually European, and index options are usually cash settled. Also, one more feature about other derivatives. So for option on index futures, they are actually in practice usually settled with delivery of index futures. So this is like option on futures. So it's multi-layer derivatives, and it's settled with the like the delivery of underlying asset instead of cash settled, and also it's usually American style. So while the index option, it's usually European options, the options on individual stocks as well as options on index futures, they are usually those two types, they are usually American, as you guys can see. Now onto the portfolio insurance example. So we actually did this exercise in the previous lectures. So here we are trying to like determine, like we're trying to hedge our equity portfolio with options contract. More specifically with index option contract. So here, when we are like, for example, when we are longing the stocks, we are going to try to like hedge that portfolio, that portfolio's market risk by holding the stock index, sorry, not really by holding, but like actually by shorting. So by shorting the stock index option. So here, we know that the portfolio value so is $500,000, and beta is equal to 1. And the other information we know is that the index level is 1,000, and the dividend yield on both portfolio and index is the same. So in previous example we discussed in earlier lectures, we only determine like the optimal number of contracts, right? So here in this example, we are also going to determine like the strike price. So here, the scenario we are faced with this specific question is that what trade will ensure against the portfolio value falling below $540,000 in the next 3 months. So if you guys still remember, like the optimal number of contracts will be calculated as N is equal to beta times P divided by F, where beta is a optimal hedge ratio. So like if you guys still remember, the original version of the calculation is that we have a optimal ratio, like basically defined to be edge. So for equity portfolios, that edge is equal to beta. And we are using beta times portfolio value and then divided by like the value of a single index option contract. So here, let me show you guys the calculation. Also, by the way, before I do the calculation, so here, like the intuition for this hedging is that basically like instead of selling the equity portfolio, you are still holding the portfolio because you still believe that in the long term it's going to like generate positive returns. But for now you want to like get rid of like short-term market fluctuations. So therefore you do the hedging with shorting stock index options to effectively reducing your beta to 0 for the entire portfolio, including the options. Now, now let me do the calculation. So N would be equal to, so the calculation is also here, but let me just do it again. So N would be equal to beta, which is 1, and then times P, portfolio value, which is $500,000, and then divided by the value of a single options contract, and that's actually 1,000 times something. So here we know that index level is 1,000, so that's 1,000 points. But each point is having some dollar value, and that dollar value is 100. So it's every point is worth 100. Therefore, the value of a single contract would be equal to 1,000 times, so 1,000 points times $100 per point. That's how you get this formula here. And if you do the calculation, that's going to be equal to 5. Here, actually, we are not shorting call options. We are actually longing put options. Sorry about that. Of course, if we are using call options to do the hedge, that would be like shorting 5 options. Now let's calculate the strike price as well. So like the aim of those 2 examples is actually to show you guys how the dividends are going to enter into the strike price formula. But here we actually like for this first example, it's actually a simplified version. So for this simplified version, we not only have dividend yield on both portfolio and index being the same, we also have beta equal to 1. So those 2 things combined, so like beta equal to 1 and also the dividend yield being the same for the portfolio and index, like those 2 adding together effectively means that all the dividend yields are going to cancel out with each other. So we actually don't have dividend yield in the calculation, but it's merely because beta is equal to 1. Later, I'll show you guys how that cancel out of dividend yields is achieved when we see the more general formula. But for now, let's just pretend that we don't have any dividend yields. So here, we know that the insurance level required is $450,000, meaning that the maximum loss we can bear is 500,000 minus 450,000, which is equal to basically 50,000. And that's actually a 10% loss. Therefore, when we are determining like the strike price for the put option, we just use 0.9 times the strike price as 0, and that's going to be equal to 900. So 0.9 times the S0 of index level of 1,000, then the strike price of the index option is 900 points. Now, let me get. Then let's move on to, so here, feel free to check out the calculation, like remained on these slides. It's just showing that if ST drops to 880, so which like if the index point, if index level drops to index level drops, what am I writing here? If index level drops to 880, how our hedging strategy here is able to successfully lock in the portfolio value to be the exact value we desired. Actually, like you'll get that the value of the insured portfolio will stay to be $450,000, no matter what level like the index actually drops to. So no matter it drops to 880, 700, 600, 500, or 100, you're still able to lock in the value of the insured portfolio to be this exact amount. So you guys can check that out. So it's just showing a specific example that this hedging strategy is able to lock in the portfolio value as we desire. Now let's move on to the second example, like still on portfolio insurance. So here, actually, we don't change anything else. We only change the beta. So instead of beta equal to 1, now we assume that beta equals to 2. Actually, we also change other information. Sorry about that. We don't change information about index level. But now we know, so here we know beta is equal to 2. Now we know the exact number of dividend yield as well. So the exact number of dividend yield on both portfolio and index are all equal to 4% per annum. We also know that the the risk-free rate is 12% per annum. So we basically need this information actually for CAPM calculation. I will show you guys more details just in a few seconds. Now, so it's again asking us like what trade will ensure against the portfolio value falling below $450,000. So again, just a 10% maximum loss in the next 3 months. So now, because beta is equal to 2, now actually the dividend yield will now affecting the strike price. So let me show you guys how. So like all the remaining information is pretty much the same. So beta changes. So beta changes from 1 to 2. The maximum loss we can bear remains the same, which is $50,000. Now we know the exact number of the dividend yield. We also know that the risk-free rate is 12% per annum. So that's a bit of extra information, the risk-free rate. Now let's do the calculation for the the optimal number of contracts, and also do the calculation for the strike price for this beta equal to 2 scenario. So as usual, for the number of contracts, it's just equal to beta times P divided by F. And now beta equals to 2, therefore N increases from 5 to 10, right? Like remember that for the previous example, beta is equal to 1. Now onto the strike calculation. So for the strike calculation, it's trickier than beta equal to 1 scenario. So here we basically need to get the portfolio return and then derive the the index return based on the portfolio return utilizing the CAPM model. So here, if you know that the portfolio return, like the maximum, like associated with the maximum loss, it can be derived as that minus 10%. That's the loss we can bear, right? But that's actually the capital return. So in order to get the total return, since CAPM model is a relationship about the total return of the portfolio and the total return of the market, right? So therefore, in order to utilize the CAPM computation to derive the index return, we actually have to get the total return for the for the portfolio first. So for the equity portfolio, total return is minus 10%, which is the maximum loss we can bear, and then you plus 1%. So that's the dividend yield. So here, the key information is that the dividend yield is 4% per annum. You see? And also, we are hedging against movements in 3 months. So convert that 4% of annual rate into 3 months rate. That's equal to 4 divided by 4. Oh, sorry, 4% divided by 4, and that's equal to 1%. Therefore, the total return for your equity portfolio is minus 9%. Then we can utilize that to kind of derive like the return on the index, like on the market index. So for the return on the market index, we can derive that based on the CAPM model. So recall that for CAPM model, the total return of the equity portfolio would just be equal to risk-free rate R plus beta times RM, which is that's actually the total, like the total return of the index, and then you minus R, you close the bracket. So that's the CAPM computation here. So since we know that the total return from the equity portfolio is minus 9%, therefore on the left-hand side of the equation, we have minus 9%. And we know R, we also know that R is 12%, but that's still annual rates. Therefore, to convert it into quarterly rates, we have to use 12% divided by 4, and that's 3%. So 12% divided by 4. Then for the beta times equity risk premium, you just use beta of 2 and times RM minus 3%. Now we have to solve for the RM. So if you just solve for the equation, you'll get that RM, the total return of the market index, is minus 3%. Now the strike price is actually associated with the capital return of the of the market index. So therefore we have to calculate for the the capital return on market index. So capital return on market index would just be minus 3%, which is the total return, right? Remember, like CAPM is all about total returns. And here to determine the strike price, we only care about the capital returns. Therefore, we have to convert that total return from the CAPM model into capital return. Therefore, we use the total return subtracting the dividend yield, therefore minus 3%, subtracting 1%. And that's going to be equal to minus 4%. Now we can utilize that level, like return on the market index to determine the strike price. So utilizing this for like minus 4% of capital return, we just calculate the strike price as 1 plus minus 4%, therefore 1 minus 0.04, and then times S0. So 0.96 times 1,000. And that like the strike price is equal to 960. Now let me show you guys like how beta equal to 1 can get the dividend yields cancel out with each other. So here, assume that we are still utilizing the same equation, like the same CAPM equation here to derive the capital return for the market index. So here, let me show you guys. So here we utilize P. Let me add one more page. Although I already wrote it here, but let me add one more page here to help you guys better understand. So here, let's utilize P to denote the P denoting the capital return on the portfolio. And here we determine, we denote the dividend yield as div. So that's the dividend yield. Recall that for this question, it's the same, right? So like for the first example, also for the second example, the dividend yield are all the same. All the same. And then like that's the ER in the CAPM model, and you let the left-hand side being equal to R, where R is the RF, like the risk-free rate, and then plus beta times RM minus RF. Oh, sorry. Since RF is just R, so let me just get rid of that F. So now you close the bracket. Actually, instead of RM, let me just wrote that as so now you see that this RM is the total return on the market index, right? So let me just express that RM as a summation of the capital return and the dividend yield. So RM is capital return plus dividend yield. We denote the capital return on the index as M. So M is the capital return. Index. And then you, like, to get the RM, you also plus the dividend yield, so which is expressed as div. Now you also minus R, like recall that for CAPM computation, like to calculate the equity risk premium, you are minusing R, the risk-free rate. And now for the first example, beta is equal to 1, right? So once you have beta equal to 1, then you'll get that the above equation is just P plus dividend yield is equal to R plus M plus dividend yield minus R. So R cancel out with R, and dividend yield cancel out with dividend yield. So we actually get that the portfolio capital return is just equal to the market index return. So that's why, like in the first example, we are directly using 10%. So it's merely because beta is equal to 1. So portfolio capital return is equal to index capital return. Like when calculating this question, like this type of question, I want you guys to be extremely careful about like what return you are using. So it's because it's too easily confusing like the total return with the capital return. So pay attention to that, and also bear in mind that for the CAPM model, it's like its relationships between total returns, like its relationship of total return on the portfolio and the total return on the market index. Then I'm actually going to skip this page because this page is just showing you guys that how like how like the strategy we just constructed is able to lock in the portfolio value. So again, it's using the specific index level of 880. So like even if the actually even if the index level drops further, like drops to 700, 500, you like based on our designing of the strategy, you're still able to like lock in the value to be 450,000. For currency options, so like what we are replacing actually are just the Q. So like remember like all the general formulas we derived earlier, like for the boundary conditions and also for the binomial tree and the Black-Scholes model. So we're still sticking to those like for example actually not here, but like for example here, those pricing formulas, we're just using them. But now instead of using Q, we are actually replacing all the Qs with RF. So that RF, as I mentioned earlier, the RF is actually just a risk-free rate of the foreign country, of the foreign market. So also for currency options, here the S0, like in the put call parity, the S0 is actually like units of domestic currency per unit of the foreign currency. So just like this expression here, so now yep, onto the binomial model. So for the binomial model, you can see that again we're just replacing like the Q in the general formula with RF. So note that here we have two risk-free rate with R being the like domestic risk-free rate and with RF being the foreign risk-free rate. So also like for the Black-Scholes model, so we just talked about the binomial model. So for currency options Black-Scholes model, again, we're just replacing Q with RF. So recall that in the general formula for the numerator of D1, we have ln S0 divided by K, close bracket, and then plus R minus Q plus 1/2 times sigma square, and then times T, right? So here we're simply just replacing any Q occurring in the formulas with RF, since RF is the effective dividend yield for currency options. Now onto future options. So that's kind of special because that's actually option on futures, meaning that the underlying asset. So it's option on futures and the underlying assets are futures. So that being said, you are having a multi-layer of derivatives. For these type of options, of course, like the call is still like the right to buy and the put is still the right to sell. It's just that the call option will now be the right to buy the futures contract and the put will be the right to sell the futures contract. And then there are two ways of like closing out the position. So like there are two ways of settlement. So one way is that you have cash settlement. Since it's futures on options, therefore like FT would be acting like the underlying asset, right? So but not really acting like it's just the underlying asset. Recall that the payoffs from the call options was st minus k, actually greater of st minus k or 0, right? So that's a like call option on a regular underlying asset. Now for this futures option, since the underlying asset is futures, therefore we just replace st with ft, since ft is just underlying. So that's one way of settlement actually. So one way of settlement is just closing out immediately. So meaning that you enter into an opposite position, like opposite direction, but similar size of position, and then effectively your position are cash settled. You are just receiving the difference in the values of those two positions. So you are just receiving the cash. So that's one way of settlement, like closing out immediately. And the other way of settlement would be that you actually enter into the futures contract. So here, that's actually the first bullet point and second bullet point here. So so they are describing the second way of settlement for futures options. So meaning that you actually have physical delivery. So what I'm trying to say here is that future options can be cash settled. It can be having like physical delivery. So like this closing out immediately is cash settlement, and for physical delivery, for call, what happens is that the holder is going to acquire a long position in the futures contract. But recall that, like, actually, like those futures are marking to market, right? So actually, like that long position in the futures contract would only be worth, let me write here, like because of like marking to market, actually like the remaining value of that long position would actually just be ft minus 1. So that's the value of that futures contract you get if you exercise the call option and you enter into a long position. But like remember that if it's cash settled, like the cash you received is actually like the payoff of the call, right? Like the maximum of ft minus k or 0. Therefore, you have to make up that difference as well. So you have to make up for the difference between ft minus 1 minus k and the difference between ft and ft. So what I'm trying to say is that you have to make up the difference between ft minus 1 minus k with ft minus 1. So if you write it here, so that becomes plus. So meaning that, like, if you do the calculation, you'll find that like a long position in the futures contract, its difference with the payoff from call would actually be ft minus 1 minus k. So the previous settlement price, ft minus 1, subtracting the exercise price of k. So that's basically the meaning of the first bullet point here. So like if you combine those two subpoints of the first bullet point, like that's actually just ft minus k. So if you combine a long position in the futures contract with that ft minus 1 minus k, that cash payment, it's effectively just ft minus k. So it's effectively like the cash settlement only without any physical delivery value. So the f star here is just FT minus 1. Then for put, it's defined, sorry, not defined, like for put, if it's exercised, then there are again two ways to like do the settlement. So you can either have cash settlement or like physical delivery being happening. So if you are like if you go with a cash settlement only, so where you receive cash only and you are closing out by entering into a opposite direction. So what happens is that now the payoff will be the maximum of K minus FT or 0. Recall that for regular put options, that's maximum of K minus ST or 0. Therefore, we're just replacing like the ST with FT, right? So that's one way of settlement of put options, like on the futures contract. There is another way of like settlement as well. So it's just like the call options. So you can also get physical delivery. So you will have a short position in the futures contract, and at the same time, so aside from that short position, at the same time, you'll also get some cash, and that cash, like recall that due to like here due to like marking to market. So here your profit, like from the short position in the futures contract, would be let me think about it. It would actually be since here you are shorting the position, right? It's going to be the minus of FT minus FT minus 1. So that's your like immediate profit from getting the short position. But recall that like if the future option is closed out immediately, what you received is this amount. So you have to make up the difference between K minus FT and FT minus 1. So you'll also receive some additional cash, and that additional cash is difference between K minus FT minus FT, like minus open bracket, minus FT minus 1 close bracket. So if you do the calculation, that's just, oh, actually here you are subtracting minus, so you are subtracting this negative number. That actually becomes plus. So you are using K minus FT and then plus FT minus 1. And that's going to be equal to K minus FT minus 1. So that's how we get this expression here. So like this F star here is representing the settlement price at the previous day of the futures. So it's just FT minus 1, right? So here we're using F star to represent FT minus 1. Now let's go to let's just go to the next page. So here it's showing the pricing of the futures options, like via the Black-Scholes model. So here it's showing, like this page is showing the payoffs. So there are two ways to do it, like closing out immediately and receive cash only. And what the other way is you also get the physical delivery also along with some cash. Yeah, now so that's a payoff. Now let's also go to the pricing of futures options. So for the pricing of the futures options, what happens is that actually the implicit dividend yield, so futures options can be viewed as having an implicit dividend yield. And that implicit dividend yield is actually R. Let me expand a little bit more here. So F0, so remember that not really F0. Sorry about the typo here. So perhaps just the letter F. It's actually the underlying asset, right? So it's the underlying asset, and it actually has some opportunity cost. So the intuition is that in a risk neutral world, the one thing is that all the other assets, they have expected returns of R, right? So, but if you think about if you think about futures contract, since its initial value is 0, so you basically have zero zero investment, and that return on the zero investment should be 0 as well in that risk neutral world. While on the other hand, if you invest in other assets, you are going to receive R as a return. Therefore, you are having by investing in the futures contract, you're just having an opportunity cost of R, right? So since if you go with other asset, you get R as return, but for this asset, like for futures contract, in the risk neutral world, you'll get 0. So R minus 0 is your opportunity cost, which is R. And therefore, like this R is kind of having the same effect as the dividend yield, right? So both this R, not really R, like both this difference, like this difference between the futures contract's return and the return on other assets, they are all going to like both this difference and also like both this difference, or we can say the opportunity cost, and the dividend yield, they are all going to reduce your portfolio value, right? So basically by reducing like the asset price level. So therefore, this opportunity cost of R can be effectively viewed as an implicit dividend yield. Therefore, actually the calculation is really easy. So like the derivation calculation of the formulas are really easy. It's just that we are just replacing Q with R. That's one thing. And also note that I just said F is just the underlying asset, like the futures contract is the underlying asset. Therefore, we also replace S0 with F0. If you do that in the put call parity, instead of like on the right hand side, instead of P plus S0 times e to the power of minus QT, now we would be having like P plus, sorry, let me write the original version here. So this term I'm writing, it's the original version, and after our substituting of those two equations, we get that like the right hand side now becomes P plus F0 times e to the power of minus RT. Also recall that for the general formula of binomial model with continuous dividend yield, so here like the risk neutral probability is calculated differently, right? So it's calculated as E e to the power of r minus q times theta t minus d, and then divided by u minus d. So here I'm just writing out the numerator. So for these futures options, we're just replacing that q with r. Therefore, e to the power of 0 will just become 1. So that's a binomial model. Let's also go to the Black's model. So for Black's model, so for Black's model, you are still like replacing everything associated with S0 with F0, and you are also replacing like Q with R. Like so like if you compare this version of Black's model for the call option, like for the call prices, you'll notice that for C equals to, for this equation, like compared to the general version with continuous dividend yield, for specifically the futures options, we're just replacing S0 with F0, right? That was S0 for the general formula. And the same happens with, say, put option. So this was S0. Then onto D1 and D2 calculation. So yeah, I also like added the opportunity cost explanation here. So if you have some interest, you can read this on your own, but it's really just what I just said. The then you can also compare this equation with the general formula for the options with underlying being having continuous dividend yield. So if you compare this with that general version, you'll find that this numerator is nothing more than just like replacing S0 with F0. So the original version is looking like this. So ln S0 divided by K plus, I'm only writing the numerators, so since the denominator is the same. So ln S0 divided by K plus 1/2, and then R minus Q plus sigma square, and then T. So here, if you plug in Q is equal to R, then you'll get this numerator here. So here, it's really just like for the futures contract, the R is just like an opportunity cost, and therefore it's like an implicit dividend yield. So here it's nothing more than just like an application of the general formula for options on underlying asset with continuous dividend yield. So we're just like replacing S0 with F0 and also replacing Q with R. Yeah, before I go to the final page, let me like still discuss a little bit about the currency options and index options to refresh your memory. So for currency options, so all those formulas, it's also like like an application of the general formula we derived. Like let me change into another color. So those are just a application of the general formulas we derived here, like where I'm highlighting. Like for currency options, it's just that the Q will be replaced with RF, and also the S0 here, it's actually an exchange rate, and also throughout this subject, we're denoting that exchange rate in these in the form of this. So S0 is measuring the units of the domestic currency per unit of foreign currency, so domestic over foreign. Then we also, let me go back. So that's the two options we discussed, and also one more option, the index options. So for index options, it's really simple. So you just use like the general formula we derived. Again, like the general, so for index options, you just use again like the general formulas in these sections where I highlighted. Also, aside from those boundary and pricing relationships, for the options with underlying assets with continuous dividend yield, except for that, like today we also discuss about like portfolio insurance, right? So for portfolio insurance, you like for this type of questions, you need to know how to calculate the optimal number of contracts, and also you need to determine the strike price. Note that the dividends, like the dividends is going to enter into the strike price. So what I'm trying to say is that dividend is going to influence the strike price. Also, like for the portfolio insurance, you are just using like the options, call options or put options to trying to like hedge for short-term market fluctuations of your equity portfolio. Now onto the final page today. So for the final page, here it's discussing the reasons to use futures options over spot options. So futures options might have several advantages as stated here in the bullet points. So the futures options may be easier to trade. So for example, it's standardized, right? Like for also like some of the those bullet points here actually contribute to this first bullet point. So also exercising the option does not lead to like delivery of the underlying asset, right? So it's just leading to the delivery, like at most it's just leading to the delivery of the futures contract. So it does not lead to delivery of this, like for example, if you are having futures options on soybeans, exercising that futures options, you are going to just receive soybean futures, but not the physical soybeans themselves. Therefore, that actually further postpones the purchase, because if you are buying soybean futures, if you are buying soybean options directly, and after execution, you'll just get the soybeans, the physical soybeans. So that's the second bullet point. And the third bullet point, like the underlying asset may not be available for trade. Like if you think about those underlying assets, like on the futures contract, like just the soybeans I mentioned, they are commodities, right? So the commodities are like actually usually just traded in very, very large sizes. So since it's traded like in very, very large sizes, the market tend to be illiquid comparing to like futures or options market themselves. So that basically that means like the futures options are actually more liquid. So that can be an advantage, right? So that meaning that it's easier to gain your desired exposure via futures contract since the market is more liquid. Then futures options also entail lower transaction costs, since if you think about soybeans, you have to if you are just using spot options, you'll be having some like storage costs, right? If you exercise, but for futures options, you don't have to worry about that. For one that's just for one example. Then finally, if futures prices are higher than the spot prices, so that's what we call as normal market. Remember what that's what we learned in the previous lectures, right? So in this scenario, the American call on futures will be worth more than a similar American call on the spot. Why is that the case? Recall that for a regular option, like the spot option, like the payoff would be maximum of ST minus K or 0, right? And the payoff for on the other hand, the payoffs for the futures options, that's maximum of FT minus K or 0. So if we're in normal market, that means FT is greater than K. Oh, sorry, not FT greater than K, FT greater than ST. And if that's the case, actually we will be having this inequality that I'm highlighting here. So if that's the case, basically the payoffs on the future options contract, futures call is going to be like the payoff on call on futures is going to be greater than the payoff on the call on the spot, simply because that FT minus K is greater than ST minus K, which is actually due to FT is greater than ST here. So if you use a similar logic, you can also show that American put on futures will be worth less than a similar American put on the spot. So that's actually because in the normal market. So in the normal market, again, the first thing we know is that FT greater than ST, right? So that's a kind of the definition for a normal market. Now for American put, the payoff you have would be maximum of K minus. So for regular put options on the spot, that's maximum of K minus ST or 0. And for the futures the futures options, that's actually maximum of K minus FT or 0. So since FT is greater than ST, therefore the second term here, the payoffs associated with futures options, actually futures puts is actually going to be smaller since FT is larger, right? So that therefore the second term is going to be smaller than the payoffs from the regular put on the spot. So that's how we derive this sentence here. And also when future prices are lower than spot prices, that's what we call an inverted market. The reverse is true. Okay, that's all for today. So see you guys.